Hello everyone, myself Kamna Singh, Assistant Professor in Computer Science and Engineering Department in Ajay Kumar Garg Engineering College. Today we are going to discuss the topic Booth algorithm. This particular topic is taken from the subject Computer Organization and Architecture. This particular subject is actually float on cases 302 and 302H also, means in the CS Hindi and cases 302, that is a subject code of the Computer Organization and Architecture. That's why I have written both the codes. Now, in the Booth algorithm, actually the Booth algorithm is the multiplication algorithm for the signed and unsigned number. Signed and unsigned means maybe positive or negative number. We can apply Booth algorithm and get the product. Now, whatever some particular requirements we need to, that is, the first thing is that we have to know about the binary addition and subtraction, arithmetic shift and decimal to binary. As we know that we already know that decimal to binary and binary to decimal. So, one by one we can understand what are the particular requirements to understand the multiplication algorithm. After that, we are going to consider the actual Booth algorithm. Now, the first thing, binary addition. Suppose that there is a register size of A. Suppose A is the register and the B is the register, and that is the 4-bit values are there. Whatever the binary stream is there, it can be, it is, I am taking the simple example. If I want to add A plus B, simply we have to add 0 plus 0, that is 0, then 1 plus 0, and it means what? If I am adding 1 plus 1, 1 plus 1 is what? 1 plus 1 is actually, that is 2. You can say that is 2, and this 2 can be represented with the help of the 1, 0, and the 1 value will be considered here. That means the 0 will be come over here, and next is the carry will be 1. That's why whenever we are going to add 1 plus 1, simple 0, 0 is the addition of the 0. And 1, 0 is a 1, 0 plus 1 is 1. This is a simple. The last one is the 1 plus 1. In the 1 plus 1, the particular ones, 1 plus 1 means 2. 2 can be represented by the help of the binary, that is a 1, 0. And this 1, 0 having the 1's value will be considered here, and the 1 value will be going as a carry bit. The simple binary addition for this one. And when we are going to represent the negative number, because the Booth multiplication algorithm is useful for the signed and unsigned number both. So, always in the Booth algorithm, whenever we are going to take the negative number, it can be considered with the 2's complement. Whatever the 2's complement is there, if I require that A minus B is there, A minus B, then B equal to what? Whatever the value is there, that is the 1, 1 and 0, 0. This is, I have taken the example. Next, first 2's complement means, if I am going to take A minus B, it means what? The first value will be taken as it is, and the second value will be considered as, this particular second value will be considered as what? This particular B, or the second value, the 2's complement of the second value, that is A minus B. So, first of all, we are going to take the B's 2's complement. 2's complement means, first we are going to take the 1's complement, then adding the 1. The 1, 1, 0, 0, it means the 1's complement of B is 0, 0 and 1, 1. Just particular alternate this 0 to 1 or 1 to 0. So, number will be B complement. After that, B complement plus 1 gives the 2's complement. So, 0, 0, 1, 1 plus 1. We are going to add 0, 0, 1, 1 plus 1. It means what? B complement plus 1, that is this one. Actually, this 0, 1, 0, 0 will be considered as the 2's complement, and when we are going to A minus B, this A minus B will be there. So, the B complement plus 1 as a 2's complement of B. Now, A plus B and A minus B, they are simple values, that is A is the whatever the value you are considering that plus, then A minus B is there, that is whatever the value 2's complement of the second value. Now, the next thing is arithmetic shift operation. Whenever we are going to take the arithmetic shift operation, we have to take what? Right arithmetic shift. In the Booth algorithm, we are going to understand the arithmetic shift operation. In the arithmetic shift operation, when we have a value a equal to 1101, whatever the value we are taking this, then the first bit is considered as a sign bit, and including this bit, we are going to operate the shift operation. Means what? ASHR is there, this particular 1, 1 and 0, 1 is there. This 1 is actually residing here, and including this one, you are shifting the operation. Means this 1 is here, this particular 1 is here, 0, and this particular 1 will be lost. This value will be lost. So actually in the arithmetic, or we are going to take the another example. Suppose there is a 0, 0, 1, 1 is there. Fine. So first bit is including this first bit, you are taking this particular 0, and then including this bit, you are going to shift operate. Means this particular is 0 like, and next value is what? This including this 0, and next is the 0 and 1, and the LSB. LSB is the last bit of that particular binary stream, or you can say that is the least significant bit. So this particular LSB will be lost. This is the simple operation for the arithmetic shift operation. Now, the Booth algorithm. In the Booth algorithm, actually, it is worked on the signed 2's complement value. The 2's complement value means whenever the positive number is there, you are taking and convert it to the binary value. But in the 2's complement value, that is when we are using the negative value, always we are going to take the 2's complement. No other method we are using for the negative integer representation. So in the Booth algorithm, we are going to use the 2's complement representation. Next, in the Booth algorithm, we are going to use for the multiplication method, and it is useful for both the particular signed bit and unsigned bit. Now, these are the hardware implementation of the Booth algorithm. The first one is the AC register, that is accumulator register. In this particular register and the QR register, actually the result will be stored in AC and QR. There is a one particular value, that is a BR register. Suppose I want to multiply this one A into B. Suppose A into B means what? The first value A is the multiplicand and the B is the multiplier. A is the multiplicand value and the B is the multiplier. So this A particular, this A, we are going to call as a BR. This is the BR register and the B is as a particular QR register. So BR is the multiplicand, that is the first number which you are going to find the product, and the second number is called as a QR register. Second number is residing in the QR register. Next is the AC register. AC register we are going to take simply to store the result. Actually, the complete storage of the result will be considered with the help of the accumulator and QR register, AC and QR. So, if I am saying there is a 4-bit A register and 4-bit B register, it means what? Actually, the store will be what? The store may be 8 or result contain values will be 8 or 9 bits. That's why we are taking these two registers. And the next one, the last bit of the QR register, that is actually the multiplier value. This multiplier value have been considered as a QN, and the second one is the QN plus 1. That is what? That is we are taking a 1-bit flag register in this particular time. At the initial stage, we are using this as a 0. There is again a sequence counter. This particular sequence counter is also called as SC, and this sequence counter represents the number of steps, how to reach, how many number of steps you are going to use and gets the actual or final result. Now, this is the flowchart for the Booth algorithm. In the Booth algorithm, the first thing is multiplicand is in BR and the multiplier is in QR. You can say the first number, whatever the number is, suppose whatever the value is there, suppose 3 is there and next is the 4 is there. Whatever the value you are going to multiply, the first number is in the BR register and the second number is in the QR register. So, the multiplicand in the BR register and the multiplier in the QR register. Now, the next one is at the initial point, accumulator. That is what? That is, there is a AC register. This AC register will be initialized by the 0 and the Q of n minus 1. Q of n minus 1 is, that is 1 bit flag value, and this 1 bit value can be considered as a 0, and the sequence counter is the number of steps to reach the solution. Now, this is the main part of the Qn and Qn minus 1. The Qn is the last bit of the multiplier, that is the QR register hold the last bit, and Qn minus 1 initially we are consider it as a 0. Whenever the 1 0, you have to apply this operation. Whenever the Qn and Qn minus 1 having a 0 1, you can apply this one, and after that you can apply the arithmetic shift right. So, one by one we can start. When the Qn and Qn minus 1 is there, whenever the both value is same, means 0 0 or 1 1, then arithmetic shift right in the AC and QR register. Accumulator and the QR register both have a to arithmetic shift right, and then the check out that the sequence counter value is 0 or not. Sequence counter value is minus 1. After that, you have to check out that the sequence counter value is 0. If that value is 0, it means you can find the result, and that particular result will be held in the AC and QR register. In the both AC and QR register. And the next one, if the particular, when the value is 1 0, Qn and Qn minus 1, then the value is AC plus BR complement plus 1. Why we are saying this BR? When the AC minus BR, this is actually the AC minus BR. This particular value called as AC minus BR. And in the Booth algorithm, when we are going to subtract any number, always there is a 2's complement will be used. So, AC and the BR ka 2's complement means what? AC plus BR complement is the 1's complement and the 1's complement plus 1. This is actually the 2's complement of BR. So, whenever we are going to subtract any value from any register, AC minus BR, then directly you are applying the AC result will be same, and the next value, the other register value will be considered as a 2's complement, that is the 2's complement of BR. After that, the same value will be considered and the arithmetic shift right and AC and QR. If the Qn and Qn plus 1 is 0 1, then the AC plus BR will be held as a simple addition or simple binary addition will be there, and the arithmetic shift right. In the all these 4 cases, every time we have to check the sequence counter value. Whenever the sequence counter value is 0, then the result will be in the AC and QR. Now, for this particular, these are the important points. You have to remember this particular Qn and Qn minus 1. So, we Qn and Qn plus 1 is that, actually that is what? 0 0. There are 2 bits are there. That is Qn plus 1 is actually what? That is actually 2 bits. 2 bits means there are the 2 to the power 2, 4 combinations will be there. So, there is a 0 0, 0 1, 1 0 and 1 1. Whenever the 0 0, your value will be considered as arithmetic shift right of AC and QR register. Whenever the 0 1, you have to apply, whenever the 0 1, AC plus BR, you have to, AC plus BR you have to perform, and after that, whatever the result will come, you have to operate this in the arithmetic shift right on both register AC and QR. Whenever the 10 value, this 10 value will be considered, then the AC plus AC minus BR, or you can write it as AC plus BR complement plus 1. So, in the 10, AC minus BR will be there and AC arithmetic shift right, AC and QR. Next is the 11. Whenever the 00 and 11, you are only applying on the AC and QR arithmetic shift right operation. Means whenever the both voltage value or both the QN and QN plus 1 value is same, 00 or 11, then the arithmetic shift right and check out the sequence counter value. This is the complete Booth algorithm. Now, we are applying the particular some rules for the Booth algorithm. First, you have to check whenever you are going to apply the Booth algorithm, the negative number is always representing by the 2's complement. When you are at binary addition is there, the carry bit will be lost. And when after performing the arithmetic shift right, whenever you are performing the arithmetic shift right, always there is what? There is the last bit and it will be lost. And that performing this particular LSB will be stored in the QN plus 1. Whatever the LSB will be lost in the arithmetic shift right, this particular will be stored in QN plus 1. And this is very, very important point. Always remember, whenever the two numbers are multiplied with the help of the Booth algorithm, the largest one, first you have to convert into the minimum binary digits. After that, adding plus 1, that will be the register size. It means what? If I am saying there is a 3 into minus 15, you have to multiply in both the multiplication value. This is the multiplicand, this is the multiplier. This can be represented by the 2 bits. You can say 0, 1, 1, or simply you can write it as 1, 1. Minimum 2 bits will be there. And the 15 can be represented by the 4 bits. Means this particular minimum binary representation of 3 is what? That is 2 bit and this particular value. So, according to this rule, the largest one in both these value, this is the largest one value. And it can be minimum representation of the 4 bit. So, the register size will be what? 4 plus 1, this is the 4 bit. So, register size will be 5 bit. It means what? You have to represent in the binary representation this 15 value as a 5 bit and this 3 value as a 5 bit. Both values, multiplier and multiplicand, will be considered as this as a 5 bits. And the size of QR and BR is always same. If it is the 5 bit or a 6 bit or a 7 bit, whatever, but both having always same size. Now, let's start with the question. Suppose that we have to multiply minus 12 and minus 20. Fine. This minus 12 and minus 20 means this is actually the multiplier and this is what? Sorry, this is the multiplier minus 20 and minus 12 is the multiplicand. This is the multiplicand. Now, this particular plus 12 can be minimum binary digit is what? 1100 and then minus 12 can be represented by what? That is 2's complement of that value. Why I am taking this much? First, we are considering the rule this one. Whenever the two values, first find out the largest one. In this particular 12 and 20, largest one value is the 20 and 20 can be minimum representation as 5 bits. So, the particular register size will be 6 bit. Now, this particular we can find out by this register size. Now, each size means BR and QR both having the 6 bit size and the next one is minus 20 can be represented with the help of the 2's complement and minus 12 can be represented by the 2's complement. The both value will be considered. Fine. So you have to remember only two things. The first thing is this particular table, that is whenever the 0, 0 or 1, 1, then the only you have to ASHR, and whenever the 0, 1, you have to AC plus BR, or the 1, 0, then AC minus BR. Only two things will be considered. Next is multiplication, binary stream is there, and then you can represent the negative value with the 2's complement. Now, the Qn and Qn plus 1. The Qn is the LSB of the QR. QR is this particular value, that is the representation of the minus 20, and the particular Qn plus 1 value is 0. This particular 0. And the BR is the multiplicand, and that is the representation of minus 12. How we are going to find this minus 12? With the help of the 2's complement of plus 12. In the starting, you have to remember that the accumulator will be 6 bit of this particular size, and then sequence counter having the 6 particular steps to reach the solution. Now, let's start with this particular example. In this, the BR value is this one, the BR complement plus 1. Why we are going to take this BR? Because we are going to consider that AC minus BR and AC plus BR both. And this is the example for 0, 0 and 1, 1. So, let's start with this particular example, the QR register. In the initial, first you have to write the multiplier value here, and whatever the multiplier value bits, that is the 6 bit, this 6 bit will go in here. 6 means binary representation is 110, you are writing it here. Qn plus 1, at the initial stage, you are initializing this value with the help of this particular Booth algorithm. The sequence counter is n, and accumulator value and Qn plus 1 is 0. So, you are going to consider this as a 1 bit 0. Now, the accumulator having AC value having, AC register having starting 6 bit. Because of the QR register is 6 bits, that's why you are taking 6 zeros are there in the initial. Now, let's check the Qn and Qn plus 1. In this particular time, the Qn and Qn plus 1 is 0 and 0. The Qn is the 0 and the Qn plus 1 is 0. Qn is the last bit of QR register. Now, when the 0, 0, only you have to apply the ASHR with the AC and QR register. Only you have to apply. In the ASHR, AC and QR register. It means what? Whatever the value is here, you have to apply this. In the particular AC and QR register, arithmetic shift operation, it means what? Arithmetic shift right. The first bit consider it 0, and including this bit, you are shifting the operation. Means 1, 2, 3, 4, 5, 6, and this 0 will come over here. 1, 0, 1, 1, and this 0, and this particular 0 is here. The Qn plus 1 bit will be lost. Whenever you are applying this particular ASHR or this, the sequence counter value will be minus 1. This is 6. Now, it will be considered as 101. The next value again consider there is a 0 and 0 Qn. 0 and 0. Qn and Qn plus 1. When the Qn and Qn plus 1 is there, again the same ASHR, arithmetic shift right, AC and QR, both the register, you have to apply the shift operation. So, 1, 2, 3, 4, 5, 6, and this particular 0 comes over here, 1, 0, 1, 1, and this 0 is here. And again the arithmetic shift right is here, 0, 0, 1, 0, 1, 1 is there, this 0 comes over here. The 5 bit is there, this is the 6, 5, and now sequence counter minus 1. After that, again check, there is a 1, 0. When the 1, 0 value is there, you have to apply the AC minus BR. AC minus BR is actually what? AC minus BR means AC plus BR complement plus 1. 2's complement, BR complement 1 plus 1 value I have given. So, you have to write simply 0, 0, 1, 1, 0, 0. And add these particular value BR complement 1 means actually you are applying AC to AC minus BR. AC minus BR is the AC plus 2's complement of BR. Next is the 0, 0, 1, 1, 0, 0, 0. Again, you have to apply the arithmetic shift right on both register AC and QR. In the arithmetic shift right, 0 consider it here. This particular 0 come over here, 0, and 1, 1, 0. This 0 goes here, 0, 0, 1, 0, 1. And this particular 1 is here. Whenever the arithmetic shift right operation will be considered, after that the sequence counter value will be minus 1. This is actually 4. Now this is 3. Next, the 3 bit is there. Now you have to apply again the 1, 1 is there. 1 and 1. When the 1, 1 value is there, arithmetic shift right directly. So there is a arithmetic shift right of AC and QR register. Arithmetic shift right AC and QR register is 1, 1 and 1 over here. Simple. Next is 6, 5, 4, 3. Sequence counter will be minus 1. So there is a 2. 2 means 0, 1, 0. You can apply this here. Next, again check 0 and 1 is here. 0 and 1 means what? Whenever the 0 and 1, you have to apply AC plus BR. BR value is written over here. 1, 1, 0, 1, 0, 0. You have to add it simply. 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1, 0 plus 0 is 0, 1 and 1. This is, and next arithmetic shift right operation with the AC and QR. In the arithmetic shift right, the first bit consider it like this, and thus including first bit you have to shifting that particular binary stream, that is 1, 1, 0, 1, 1. This last one will be going here in the QR register, and next is 1, 2, 3, 4, 0, 1, and this 0 goes here. There is a 2, next is the 0, 0, 1. Next value is, again consider this, Qn and Qn plus 1. Qn is 1 and Qn plus 1 is 0. Qn and Qn plus 1. The 1, 0 means AC plus BR complement plus 1, or you can say AC minus BR. So AC plus BR complement plus 1 is 0, 0, 1, 1 and 0, 0. You have to simply add. 1 plus 0, 1. 1 plus 0 is 1, 1. 1 plus 1 is 0. Carry bit is 1. 1 plus 1 is 0. 1 plus 1 is 0. Here in the Booth algorithm, whatever the carry bit will be there. Here is the carry bit, but the carry bit will be lost. Or you can say the carry bit will be discarded in the Booth algorithm. Next, arithmetic shift right. In the arithmetic shift right, AC and QR will be there. In the AC and QR means the first bit is like this, and including this bit you are going to consider it here 0, 0, 0, 1, 1, this 1, 1 over here, and this 1 over here, and there is a 0, 0. Whenever the sequence counter value will be 0, then whatever the result consists is AC and QR, means the result will come over here, this particular 1, 1 and 0, 0. So actually you can verify this particular result as we have what? We have a minus 12 into minus 20 was there. That is a multiplier and multiplicand. That means actually that is a 240 value. And 240, the representation of the binary is 4 ones and 0, 0. And the result will be what? Actually, it will be stored it here in the AC and QR, not the value of the Qn plus 1. Always remember, the result will be stored in AC and QR only. This will be your result. Now, this is a simple example. The first thing, first we have to repeat this particular. Initially, Initially, in the Booth algorithm, you are taking the BR and BR complement 1 plus 1. Whatever the size of the QR register, you are taking the 6-bit. If the QR register having the 5-bit value, you have to consider as accumulator having a 5-bit value. And sequence counter is the number of steps to follow these particular and getting the result. The next value, first, we have to always consider that QR and Qn plus 1. 0 initializing is there. The QR having the last significant bit and next 0, 0. So, ASHR is AC and QR. You are applying this simply arithmetic shift right. Again, there is a 0, 0 value. So, you have to apply this one. Simple. I am just repeating that particular example again. And next, when again you are going to check this 1 and 0. Then next 1 and 0, 2's complement of the BR will be there. And next is the value is this. So final you are getting this particular result. Now always remember in the Booth algorithm, whatever the multiplicand on multiplier, if these particular value, whenever the both are positive or both are negative, the result in the AC and QR. If any of the particular value is negative, even in the multiplier or a multiplicand, always whatever the result come over here in the AC and QR, you have to 2's complement of that particular result and then you get the final result. Always remember this for the final result composition. When both the values is same, that is always the result will be AC and QR, positive or negative. Either one of the value of the multiplier or multiplicand having a negative value, so result will be negative. So this particular value can be stored in the AC and QR. 2's complement of this particular value and then taken this particular. So this is the performance of the Booth algorithm. It is faster and it is reduces the number of actual value. So thank you.